Hi folks. Modern computer screens typically have a color depth of 8 or 10 bits per channel, producing millions or even billions of colors. But in the deep and ancient past, when dinosaurs roamed the earth, we had a much more limited color palette, sometimes only black and white. To keep from going mad in those dark times, we invented dithering. Dithering is a technique for emulating the appearance of a large color palette, when you only have access to a small palette. These days it's not needed as often as it used to be, but it still has its use cases. It's a common visual effect in retro-style video games, like Return of the Obra Dinn. It's also important for e-ink screens, which have a much more limited palette than ordinary screens. And even if you have a large palette, you can still get visible banding in some situations, like dark color gradients. I got interested in dithering for a game project I'm working on, which uses black and white graphics. In this video, I'll talk about a novel dithering algorithm I came up with, which might just be a contender for Best Dithering Algorithm in the World! With a few caveats. There's a companion blog post that goes into more technical detail. Link in the description. Despite being a relatively simple seeming problem, there are heaps of dithering algorithms, with various trade-offs and producing different quality outputs. Broadly speaking, there are two categories of dithering: ordered dithering and error diffusion dithering. Our goal is to reduce the palette of this test image, and for simplicity we'll just reduce it to black and white for now. Every pixel in this image has a value between 0 for black and 1 for white. A naive approach would be to set all the colors darker than 0.5 to black, and lighter than 0.5 to white. But you can see we lose tons of detail if we do this. We can try changing the threshold, but we're always going to lose a lot of detail. Ordered dithering is a simple improvement to this naive approach. Instead of using a fixed threshold for the whole image, we use a different threshold at each pixel. For example, we might try randomizing each pixel's threshold. We can represent the random thresholds as a mask like this. We overlay the mask on the original image, and then at each pixel, if the original pixel is darker than the mask's pixel, the output pixel is black. And if it's lighter, the output pixel is white. Ordered dithering using this kind of mask is known as white noise dithering. The results are better than the naive approach, but it still looks pretty terrible. It's so noisy that a lot of the detail is still being lost. The threshold mask doesn't always have to be the same size as the original image. Bayer dithering uses a small mask with a power of 2 size like this, so we just tile it to fill the original image. This mask is mathematically easy for a computer to calculate, and produces these very regular and distinctive dithering patterns. Depending on what you're doing, these patterns may be just the nostalgic feel you're looking for. But if you want something more organic looking, your best option might be void and cluster, also known as blue noise dithering. It's similar to white noise dithering, but uses a noise mask that looks like this. Without going into the technical details, this noise has been carefully crafted to avoid the patchiness that appears in pure white noise. You can see what I mean if I blur the two noise masks. Void and cluster dithering produces very organic looking results, though it does still lose some of the details. The algorithm to generate the noise mask is quite complicated to implement, and it takes a long time to run, so you'll definitely want to pre-bake an appropriately sized noise mask ahead of time. For better detail preservation, you can try an error diffusion algorithm. The basic idea of these algorithms is that after you snap a pixel to the nearest palette color, you take the error, that is, the difference between the input and output colors, and you propagate it to the neighboring pixels. In this case, snapping made the pixel darker, so its neighbors are lightened a little to compensate. Different error diffusion algorithms make different decisions about which neighbors you propagate the error to, and how you distribute the error between them. The order you process the pixels also matters, since you can't propagate errors to pixels that have already been snapped. The most famous error diffusion algorithm is Floyd-Steinberg. It iterates through the pixels line by line and propagates errors to the immediate neighbors that haven't been processed yet, using some specific weights. It produces fairly organic-looking results that preserve more detail than ordered dithering algorithms. There are a lot of interesting trade-offs in the two classes of dithering algorithms. I've already mentioned the first. Error diffusion usually does a better job of preserving details than ordered dithering, because the information lost when a pixel is snapped to a palette color is propagated to its neighbors in the error value. Modern computers have a module called a GPU that is designed to run tens of thousands of small programs simultaneously. So if you can break your program into small independent identical chunks, you can get a huge speed boost by running it on the GPU. This is essential for real-time applications like video games. For ordered dithering, since each output pixel is independent and just compares the input pixel with the corresponding mask pixel, it's extremely parallelizable. But for error diffusion, every pixel depends on its neighbors, which depend on their neighbors, and so on. So we have to process the pixels sequentially. This means it's difficult or impossible to run these algorithms efficiently on a GPU, and it makes error diffusion algorithms unsuitable for real-time applications. So error diffusion is a good choice for pre-processing your game assets at build time, but not for dithering rendered frames of your game in real time. Another trade-off is temporal coherence. What do the results look like if you make small changes to the input image over time? For ordered dithering algorithms like Bayer, or void and cluster, as long as you reuse the same mask each frame, the temporal coherence is great. But error diffusion suffers here. With errors propagating across the image, the value of a pixel on one side of the image can depend on a pixel on the other side. This is terrible for temporal coherence. For the same reason, you can't do incremental updates of an error diffusion dither. The last trade-off I'll talk about might seem weirdly specific, but it does come up from time to time. Usually when you're reducing the palette of an image, you're clamping it to a regular grid of colors in some color space. And any dithering algorithm can handle that. For ordered dithering, you can just scale the thresholds to the size of a grid cell before applying them. And for error diffusion, you simply snap the color and calculate the error as normal. But sometimes your palette doesn't form a grid. This comes up most commonly in palette optimization. For example, in an animated GIF, you're only allowed 256 colors, but they can be any colors you want. So a good GIF encoder will select optimal colors based on the colors of the input video. Those optimal colors probably won't form a grid, which restricts what dithering algorithms they can use. Error diffusion still works fine, because finding the nearest palette color is still straightforward. But we can't use ordered dithering in this case, because it's not clear how you would apply the thresholds here. So error diffusion supports any palette, but ordered dithering only supports color grids. For my application, I didn't need real-time rendering, so I focused on error diffusion. The main downside of Floyd-Steinberg, in my opinion, is that it has some strange artifacts and patterns that void and cluster avoids. And these artifacts have very clear directionality based on the iteration order. Here are some other iteration orders for comparison. If you know what to look for, you can tell how the image was iterated just by looking at the artifacts. This is what gave me the idea for my dithering algorithm. The directionality of the artifacts and patterns bothered me, so I figured why not just randomize the iteration order? That's pretty much all there is to it, really. Iterate through the pixels randomly, and propagate the error to all the neighboring pixels, splitting the error evenly between the ones that haven't been processed yet. I call it Dizzy Dithering because of the way the iteration zooms crazily around the image. There are some tricks to doing this efficiently, but I'll leave those details to the blog post. So what do the results look like? I think the results are pretty great. There's no artificial structure visible in the image, the dot patterns look organic, and it does a good job of preserving details. Comparing it to void and cluster, I think Dizzy Dithering looks equally as organic, and does a bit better job at preserving the details. It's really easy to implement too. You can do it in about 50 lines of code. There's a link to a Python implementation in the description. Now let's take a look at temporal coherence. Remember that ordered dithering had good temporal coherence, and most error diffusion algorithms had bad coherence. But if you use the same random pixel iteration order every frame, Dizzy Dithering actually has quite good temporal coherence. So this is an area where Dizzy Dithering significantly outperforms other error diffusion algorithms. So I think in future, if I need an error diffusion dithering algorithm, I'll reach for Dizzy Dithering instead of Floyd-Steinberg. Since my game project doesn't need real-time dithering, I'll leave it here. Dizzy Dithering seems to have the same parallelization issues as other error diffusion algorithms, so void and cluster remains the go-to for high-quality real-time dithering. At least, that's what I thought until Peter got in touch. He needed real-time dithering, and figured out a way to parallelize Dizzy Dithering. I'll link to his blog post in the description, but the core idea exploits the fact that the errors in Dizzy Dithering don't actually propagate very far. This animation is showing what real error propagation looks like. Theoretically, if you get very unlucky with your iteration order, an error could propagate all the way across the image. But that just doesn't happen in practice. This is why Dizzy Dithering has good temporal coherence. Before I go any further, I should just lay out the actual steps of the algorithm more explicitly. First, create a list of all the pixel coordinates in the image, and shuffle it. We also need to keep track of the set of pixels that are done. Then, for each pixel in the shuffled list, mark the pixel as done, snap its color to the nearest palette color, calculate the error, and then split the error evenly between each of the neighbors that aren't done. By neighbors, I only mean the orthogonally adjacent pixels. I experimented with also propagating errors to the diagonals, but this makes parallelization twice as hard, and doesn't make much difference to the results. Okay, so an error only propagates until it hits the pixel that has already been processed. How far is that on average? To find out, I ran Dizzy Dithering on a large image and measured the distances that errors propagate through the image. I knew the errors didn't travel super far, but even so I was shocked by the results. Most of the errors only propagate a few pixels, and 99% of the errors travel less than 8 pixels. So let's say we cap the error propagation to 8 pixels. How does that help us parallelize the algorithm? Well, that means we can divide the pixels into 8 groups and run the snapping and error propagation for every pixel in the layer at the same time on the GPU. The new algorithm looks like this. We randomly divide the pixels into 8 layers, then we iterate through those layers one at a time, and process all the pixels in the layer at the same time on the GPU. The pixel processing steps remain the same. And actually, while we're pre-calculating the layers, we can also store which pixels are done and which aren't in our layer data, so we don't need these bits anymore. Now, there's a bit of a trick to dividing the pixels into layers. If 2 pixels in the same layer are too close together, they might try to propagate their errors to the same pixel. This is called a race condition, and it's bad, because the result is unpredictable. So when we're dividing the pixels into layers, we have to be careful to make sure every pixel in each layer is at least 2 pixels apart. This is a bit tricky, but I found that a randomized greedy algorithm worked quickly and reliably. And we only have to generate this layer mask once, then we can reuse it every frame for real-time dithering. More details in another blog post in the description. Here's what one of these layer masks looks like. Suspiciously similar to a void and cluster mask if you ask me. Maybe this algorithm could be adapted as a cheaper way of generating void and cluster style noise. But that's a quest for another day. Alrighty, so we've got our layer mask and our new layered Dizzy Dithering algorithm. So does this actually generate a good dither? Yep, the results are pretty much identical to ordinary Dizzy Dithering. So now that Dizzy Dithering can be run in real time, is this the best dithering algorithm in the world? Well, sort of. But there are some caveats. Firstly, what looks better is subjective. Sometimes you want the classic look of Bayer dithering. Secondly, although Dizzy Dithering has the same big O complexity as any other dithering algorithm, it's a bit slower in practice. Floyd-Steinberg is faster and uses less memory than ordinary Dizzy Dithering. And the layered Dizzy Dithering algorithm's multi-pass approach is slower than a simple ordered dither. Whether or not this matters depends on your use case. Finally, there are use case specific tweaks that can be applied to any dithering algorithm to improve the results, such as an edge enhancement filter. I've only been comparing baseline algorithms. At the end of the day, dithering is more of an art than a science. That's probably why it's still possible to find new ways to arrange these black and white pixels half a century after the problem was first considered. If you do decide to use Dizzy Dithering in your own project, let me know. I'd love to hear about it. Thanks for watching.